So basically, I'm going to try to connect the two topics that we've heard about a little bit in my presentation. So we've heard a very nice presentation by Seth that is asking some really fundamental research question about how we can have emergent language between different type of agents, and we've heard some really detailed explanation about how to collect the data and do data fusion in the context of wildfire monitoring in particular. But I'm going to try to abstract from that a little bit in order to make them more connected to each other by talking specifically about how we can use collective artificial intelligence in the context of gathering this data, and in the hope that eventually we can use this sort of collective intelligence augmented with the type of communication capability that Seth was talking about that could emerge even in a heterogeneous population of robots. So I wanted to first tackle the question that can be called the elephant in the room. So basically, is promoting robots as an environmental protection tool even a remotely good idea? And this is actually an open question, and I'm not pretending that it isn't. There is a major problem in conservation biology in general. I'm talking here specifically not about protection against wildfire or something like that, but conserving wildlife, where the economics are very complex and challenging. So this is the reason why there is no universal answer to this question. Basically, one aspect of the environmental conservation problem is that many of the ecosystems that are worth protecting are in third world countries. And in these countries, using expensive and high-tech solution usually doesn't add up. Most damage that is done to the environment is done by people who have no other choice due to their economic circumstances. So if you think about some of these natural parks that we have in Africa or something, there is poaching. The reason why there is poaching is that people need poaching to survive. That's the only way that they will be able to sustain their families. And so because of that, there is a thinking in conservation biology circles that is basically you don't need high-tech solution. What you need is to provide people with a way to move away from these environmentally destructive activities, for instance, by giving them a good job as a warden or by giving them other opportunities and better infrastructure that will allow them to move away from this destructive behavior towards the environment. And therefore, we don't need all these fancy gadgets. And actually, if you at first sight, this looks like a very sensible and ethical standpoint. Because you can, and in the short term, it's certainly something that we need to do to try to provide alternatives to these environmentally damaging activities. However, in my opinion, it is also very short-sighted because if you cannot assume that this short-term solution will keep being a solution if the development follows its normal course. Because when the economy starts developing in these countries, you end up in a situation where they are right now in Southeast Asia, for instance, where pollution and degradation of the environment is still a problem, because that's a natural byproduct of socioeconomic development in all civilizations. We have done it in the West. This is happening in Southeast Asia, and eventually it's going to happen to these other regions as the economic circumstances of people is improving. They actually start polluting more, not less. That's what we did, we in the West. The reason that this is a problem in general is that, like any other species, humans are an invasive species. This is not a moral judgment. It just means that when people expand into a new area, they become part of the ecosystem and they challenge the natural equilibrium that existed before humans moved into that space. The best way to protect wilderness is to stay away from it as much as possible. That is, at the end of the day, the best way to save an environment is to not have humans interfere with it so much that they would actually pollute it, like in this famous picture, which is this town in Russia that has been where you have polar bears living on trash, because that's basically where humans and wildlife meet. So the question then becomes, how do we reconcile this realization with the aspiration that we all have as natural creatures to actually be connected with our environment? And that is, I think, where robots could be part of the solution, because they could be our eyes and ears where our actual physical presence is disruptive. robots are not biochemical machines like us. So they don't generate the same type of waste that we do. They don't interact with the environment in the same way we do. There is a possibility that we can design them to minimize harmful interaction with the environment, while at the same time being able to observe the environment in the way that we aspire to do. So I think in that sense, robotics could be actually a nice approach to environmental conservation and a natural observation that is not as invasive as actually sending people into the area. Right, so, but this is kind of a philosophical long-term view on why robots could be a good idea for environmental monitoring. In the short term, in the here and now, we have more direct questions to answer. So if even in principle, substituting robots to humans as observers and protectors of the environment can be controversial, there are many circumstances in which you can see that this would be a good idea even in the here and now. So there are wilderness areas that are harsh or dangerous, and keeping them pristine means keeping them that way. So for instance, you can have deserts, you can have Arctic conditions. So in a way, the environment there is quite hostile to human life. And if you send people to protect this environment, you basically give them a harsh environment to live in. Some environment protection are also exhausting tasks, are also exhausting, stressful, or repetitive. It's no secret that actually being a warden in the Serengeti is a dangerous job. You can actually be shot by poachers. The same happens in the Amazon basin, mostly not because of poaching, but because of illegal logging and mining. People get killed because they interfere with these illegal operations in these regions. And of course, finally, and most obviously, since we are talking about this in Finland, there are also natural reserves in the developed world where the reasoning about labor and infrastructure being cheap and therefore being a better option than scientifically advanced technological solution does not add up anymore. Because, here, the cost of stationing someone with the right working conditions in the wilderness is not negligible compared to as it would be in some other parts of the world. So then I started thinking, so how do I illustrate that? And I thought that a good proof of concept may be to test an autonomous drone force in a national park where people and wildlife coexist in a recreational context rather than in an exploitation context, as in the example I've given before. And then we could actually try to explore the advantages of this concept in that context. So in these environments, there is no criminal activity such as poaching or illegal mining, etc. Finding and assisting lost visitors is basically the most serious challenge you're going to have. And most of the harmful behavior that humans have is basically due to negligence rather than deliberate attempt at damaging the environment. It's like littering or starting a fire where you shouldn't, and that sort of things. So you don't have this kind of antagonism potentially between the wardens and the other people in the environment. Hence the idea of what I call wild swarms, which are basically a certain kind of swarms that actually relate more to the idea of squad that Seth was talking about in his talk. In the military, for instance, swarms are a hot topic because there are many potential applications for this technology. However, in most cases, what is intended by the word swarm is not necessarily what we call swarms in biology. For instance, you have these light shows that are currently being shown as an example of swarm behavior by drones. They are very popular in places like Dubai, etc. And these things are actually not really collective intelligence at all. They're basically just a set of physical devices that follow a choreography that is very precise and has been established beforehand. They don't know each other. They don't interact with each other. They just follow a predefined course. And that creates this nice 3D picture in the sky. But there is no collective intelligence principle involved. And even when these principles are in use, like for instance, you can have again military application, you can have formation flying, where it's important for drones to know where they are with respect to each other, to be able to fly as a swarm. It's usually on a very short period, which again is something that Seth touched on, and it's in the context of a single one-off mission. So they observe that particular fire event. Not in general fighting fires over Finland for the entire year. It's a very different proposition in a way. They're deployed specifically for one particular kind of event. And in contrast, biological swarms do not work like that at all. Whether we are talking about ant colonies or beehives or something like that, they are a completely decentralized system. Their adaptive behavior doesn't result from any kind of pre-planning, but from self-organization. And maybe even more importantly, they cooperate and operate over a very long time scale. They operate in a way in which individual workers are performing different tasks from one day to the other, or from one part of their life to the next, in the case of H. polyethysm. And even though these behaviors emerge as a result of the same type of positive and negative feedback, they need to adapt over a very long period of time to be able to sustain the colony over more than the time that it takes to do one single swarming mission, if you see what I mean. So the idea here is that we could have an autonomous drone force in charge of environmental protection that would behave more like a real natural hive than like a swarm in the context of one particular mission-specific application. So you would have a population of drones that lives in the national park and keeps it under surveillance over a very long period of time, managing all the aspects of the life of the swarm that are necessary to manage in order for it to operate over this extended period of time. So here is a scenario I came up with to try to illustrate that, and I will show you, it will become clear in the demo why I chose that one. Imagine that a new international park is created in Northern Europe. No hints about where that might be. There is no settlement, no road access to this area. So it's real wilderness with the same kind of wildlife that has always been there, etc., etc. And therefore, it's really pristine nature. But of course, humans are curious, and that means that it becomes very popular among extreme hikers, not your average family trip in the wilderness, but people who are willing to live and camp for a week or so in that environment. Of course, that means that there is potentially interaction that might be harmful to the hikers or to the fauna of that environment. However, because as I said, the hypothesis is that there is no connection to this area, there's no roads, there's no infrastructure, etc. It's actually complicated to put a human warden force there for the long time. Therefore, let's say that the government realized that it would both be costly to install wardens in this area, but it also, in a way, would be kind of contradicting the very nature of a national reserve, which is basically to minimize the impact that humans will have there. If you start building a ranger station in the park, you're damaging the very thing that you're trying to protect. So maybe a good solution would be to try this high-tech solution of having a drone hive living there and see how that would work. So basically, instead of being put under the supervision of human wardens, the reserve is placed under the care of an autonomous drone swarm over a long period of time. And the mission of the swarm is very simple. At a high level, is to patrol this territory that is put under its care for an indefinite period of time, detecting and discreetly monitoring hikers and animals that are of interest for some reason. So not necessarily every raccoon, but some like a bear, for instance, might be something worth following, and to ensure that both are kept safe from each other and that their well-being is being preserved in the context of their interaction. Right. So if we move away from this kind of high abstract goal, what is the challenge in terms of swarm robotics here? In a nutshell, what you want to be able to do is to maintain the best possible situational awareness by discovering and monitoring all the relevant actors in this environment over a long period of time. These actors might be humans and wildlife, as I said. Events might be something like a fire starting, as we've seen in the previous talk, or maybe a flood or whatever. So the important thing is that you don't know exactly a priori when that will happen in the lifetime of the swarm. It might happen 3 months after the swarm has been deployed, or it might happen 3 years after the swarm has been deployed, or 3 days. So you need to be able to prepare for that and react to it when it happens, even though you don't know when that's going to be. So this implies a number of other things. So first of all, you have to manage the available resource, so the number of drone units that you have, the landing pads that they have, where they can also recharge their battery, that sort of things, in order to guarantee that the swarm survives in the long term, and not just in the context of that single mission that we were talking about earlier. Second, you need to be able to do things like generate flight plans that are compatible with the range of a drone. So it cannot fly beyond the point where it cannot come back to base and it will crash in the forest. And you need to do that in such a way that you also leverage division of labor so that not two drones go patrol the same area and leave another area completely unvisited. So you need to be able to take into account this aspect as well. And also, finally, when you find something unusual and you have to move away from your routine patrolling of the park, you need to be able to take the action that is required in order for some useful action to take place. Like, for instance, you might want to be able to switch from an exploration behavior to a monitoring behavior when you detect something of interest. So stop your normal trajectory and start hovering above the event, report it to the base, and do something about it, something like that. Right? So basically, what I've been doing is a little simulation demonstrator that will basically show you how this could be done. It will actually, and I will actually probably better if I go to this slide. So you have this this is my best attempt at reproducing a nice lake and forest environment. So basically you have different types of symbols in that environment. Here you have this little helicopter landing pad symbol that indicates the position of one base where the drones can land and recharge. There is a fixed number of landing pads, so there is a reservation system whereby a drone is guaranteed that it can land and find a place to recharge when it reaches that particular base. Then you have drones in the system that are obviously the icon of a drone. They're surrounded by a circle that is the range at which they can detect events, like a hiker is there or a bear is there or something like that. And then they create these flight plans that are visualized at this trajectory here in this yellow line. Another thing that you see in the demo is this fog of war concept, which basically means that a place that has been visited a long time ago or not at all is actually covered in this kind of fog that basically tells you that you don't have information that is accurate and up to date about that particular region. So for instance, in the demo, you see that you have this grayed out area where you have no good information. When you have the bright green or blue area, that means that you have up-to-date information about that particular zone. And you will see how the flight patterns of the drone, kind of clear the fog of war in a particular pattern, depending on how they operate. And then finally, you have, as I said, different types of terrain here. You have essentially two in that one only. You have lakes and you have forest. Both are passable by drones, the assumption being that they can fly over water or over the top of the trees. But the other agents in the system, the hikers and the bears in my demo, are able to only walk in the forest area, so they have to go around the water bodies in order to go from A to B. And you will see during the demo that you can have two types of other actors so far in the demo, hikers and bears. And if you have an empty symbol, that means that you know in the simulation that the hiker is there, but the swarm doesn't because it hasn't been detected yet. And when it's a full symbol, like in the bear in this case, it means that it's being actually monitored. It's being located, at least by a drone. And when it's full, it is within the detection range of one drone that is currently airborne. So that's the symbol set. So now I'm going to try to move to the demo, which is going to be the tricky bit. So I should probably stop. You can stop that. Right, that is better. Right, there we are, more or less. UK, you can still see that? Yep. So now basically you have this area here that is part of the park. Actually, I'm going to make it a little bit more interesting. So by drawing some more complex borders to the park that is more tricky to navigate for the swarm. It's okay. So now the system is preparing by doing a little bit of calculation that it's going to use in its navigation later. This is not a Microsoft progress bar, it's a real progress bar. When it reaches 100%, it will be finished. So it's not that long to wait. And so basically, one of the rules is that the drones can never exit the national park. So basically, if they have to fly from here to here, they cannot go across. They have to find a way around it because that's meant to be, airspace that is not safe for them to fly into. So now I position a base here. So that is a point where drones can land and they can charge. Each one of these bases currently has 4 pads. So you can only accommodate 4 drones with 1 base. So if I fill the system with the maximum number of drones, at the moment they basically enter the park by randomly located positions on the border. And I start the simulation, so you will see them flying towards the base where they're going to recharge for the first time. And if I show the fog of war, you can see that basically they're clearing it along the path. But of course, the fog forms back again after some time, indicating that you need a new reconnaissance mission there to make your information more up to date. So I'm going to speed that up now so that it takes not forever. And so that's basically at steady state. The system is basically recharging for some time, then sending a mission. Then the drones are flying around. At this point, they are just doing a kind of what they call persistent random walk. So really trying to optimize their behavior. But if I take this one, cooperation, it actually starts using some more interesting navigation process that essentially tries to maximize the amount of fog of war that they can clear with respect to each other. So they take into account the fact that one of them has been exploring one region, and then there's more that makes them more likely to go in another direction. And as you see, you will start to have this typical behavior where they go far to the border and then they follow the border a bit. And then only when they reach the limit of their operational range, they fly back to base. So that's basically the best you can do with only 4 drones, because of course, I should have said their autonomy here is 15 minutes for one flight, and then they have to recharge for 15 minutes. So I assume that the time for charging and the time for flying were the same. So at the moment, that's the best they can do. But what I can, of course, add is I can start putting more bases. So first of all, even though I have only 4 drones, you will see that they start using them as landing pads, which means that they can effectively go further because they don't have to go back to base. They can now land in one of these faraway bases, and that makes effectively the area more accessible to them. And again, I didn't change anything to the algorithm, right? I just said there is a new base there, you can use it, and the system, capitalizes on this automatically. And now, of course, that means I also, because I have now 5x4, 20 landing pads, so I can add more drones. So if I add, so that's 8, I'm going to put 12 in there. So now basically, as you see, the fog of war is almost completely gone because now there are enough drones to, again, be able to clear the fog permanently and still using this division of labor to try to not overlap too much so that they do not duplicate information, but they try to keep information up to date everywhere at the same time. Of course, again, one important feature here is, again, I didn't change the rules or anything. I just told the swarm, you now have 12 drones instead of 4. Do the best you can with it. The algorithm is the same. It's just doing a better job now that it has more resources at its disposal. Now, what happens if we start having interesting things to do? So, for instance, I had one hiker. So, hiker here is going to go from one part of the park to the other, still not be located. That's a problem with. It's been seen once, I think. That's the problem with a real simulation. It was seen once again. Now, the rule at the moment is that basically they just report that they've seen the hiker, but they don't do anything about it. They just carry on their route, and they don't do anything. Now, if I turn on another feature of the swarm, which is recruitment, then what happens with respect to hikers is that when a drone detects a hiker, that actually creates a waypoint in the collective mind of the swarm, if you want, that the next drone should actually go through that place. And of course, since that was the last known location of the hiker, it's likely that the hiker is not very far from that point. And statistically, you will see that you will typically see them multiple times and observe them as they move along. So let me try again. So yeah, So you lucky? Okay, that's better. So of course, and I will come back to that a little bit later, one of the problems with these things is that you really need to use statistics to know if it's better or worse, because there's a lot of noise in your system. So it's difficult to make sure that it will show what I want to show. The last thing I want to show you now is what if I add a bear. So the difference between a hiker and a bear in the swarm's mind at the moment is that the bear doesn't need to be just spotted, but it needs to be monitored while it's there. So just, for instance, so that you are able to warn visitors that there's a bear nearby. So now what will happen when I have a bear, and if it gets noticed, again, I hope the simulation is not going to betray me, is that the drone that sees the bear interrupts its flight, starts hovering near it, and only when it reaches a limitation in terms of range, it goes back to base. And again, there's a recruitment mechanism whereby another drone should be dispatched to the location of that where the bear was last seen, and again start hovering around above it. So like that. See, so that's what it's doing now. So another one. Now it's been lost. It's left the park. So another one. So basically, you see what's happening now. Basically, essentially, most of the time, the hikers are spotted several times as they cross the park, and the bears, once detected, are kept under monitoring by all the drones that relay each other to keep it under surveillance beyond the time that they're able to fly individually, which again links to this long-term survival of the swarm that is capable to perform this mission over a long period of time. Right. Let me try to go back to my slides now, which of course I have closed in the process. Right. So as I said, one of the problems that we have with this sort of system is that it's difficult to measure the performance using the conventional methods. Designing a good swarm algorithm, contradict me if you disagree, Seth, is sometimes more art than science, in the sense that you think that something might work, and then you try it, and then you try something a little bit different, but there's not always a very proven methodology to actually design the algorithm. However, there are very good tools and methodologically sound methods tools to evaluate the performance of these algorithms. It just so happens that they're usually not the ones that are the most commonly used in engineering. And that's an issue. Because in general, in engineering, you have this concept that you need to think deterministically. If you design a machine to do something, either it will work or it will not work. If it doesn't work, that means that you've made a mistake in your design, and you go back to the blueprint and modify it. In the case of these collective intelligence systems, very often you get a response that is neither perfect nor completely imperfect. And it's much more tricky to say, does it work or does it not work? It works more or less, but does it work more or does it work less? And that's basically the kind of design methods you have to follow in order to design these swarm algorithms. This is the reason for this difficulty to predict how the swarm is going to behave, and the difficulty to assess its behavior and performance with just one or two runs, is that it's very sensitive to initial conditions. There is a lot of noise in the system that is deliberately introduced into it to augment its adaptability and plasticity, and also it has a memory. So, which means that when something happens that involves the swarm making a decision, that will affect its next decision, and this next decision will affect the next decision, and so on and so forth. So that means that you very quickly drift away from what you could have predicted because of this kind of cascade of mutually referential decision making. That's what I'm explaining in these small bullet points at the bottom there. Happened here. So as a result of that, a single experiment or simulation run is usually essentially useless. What you need to do is statistical analysis over sometimes very many runs if the noise level is very high. And I haven't had time to do a full exploration of the performance of the algorithm I just shown here, but I have some examples to show you that I hope will shed some light on the methodology. So this is how I collected results about the density of the fog of war on average in the system for different types of swarm infrastructure. So in the first case, I have one base that has 16 drones. So it has 16 landing pads, this one, and it uses random walk. And so you've got the blue line is the average amount of fog of war. The dashed blue line is standard deviation. The red one is the highest density of fog of war, and the green one is the lowest density of fog of war. So green is good, right? That's the best the swarm ever achieved, is when there was the least possible fog of war left in the system. And so, of course, at the beginning, the system is completely unknown, so it starts at 1, and then over time it drops, and then you see it's stabilized around this value, and you can see how switching from random walk to cooperative exploration gives you an advantage, right, in terms of the amount of fog of war that remains in the system. Again, if you make other comparisons, so this one is for not one base, but 4 bases. So there's the same number of drones, but now they have multiple options in terms of where they can land. So again, you can see how it will improve performance in the case of random walk and in the case of cooperative exploration. But of course, the best is that you combine the cooperative exploration with the fact that you have more bases, and you get the best possible result so far. But now, if you can compare what happens if you have cooperative exploration with 1 base, cooperative exploration with 4 bases, and all of these give you different results, and you basically have to analyze all of them in order to be able to say exactly which system works best and why. And even then, it's not so easy. This is where I keep the same number of bases, but I diminish the number of drones. So if you have same number of bases, different number of drones, random walk versus cooperative exploration, again, you have a different signature. And so by doing all these numerical experiments, you start building a picture of what the swarm is good at when there are that many drones, that many bases. And that algorithm is being used versus that algorithm, and so on and so forth. And that's basically how you design the system to become better and better by trial and error, essentially. Now, one last thing I wanted to show you, because that's work in progress, but it's still amusing and interesting, I think, is this is the amount of fog of war in a simulation where I had 4 different phases. In the first phase, it's the same as the picture you've seen before. There is no bear and there's no hiker. So this is basically what we had before. So just the drones are just in the routine patrolling behavior. Then between 10,000 and 20,000 time steps, there are only hikers. And that affects the amount of fog of war. Now, interestingly, I was expecting this to increase the amount of fog of war, because I thought, well, basically now you have some sort of extra constraints that the drones have to go back to the last known location of a hiker. That means that they will not be able to explore the environment as efficiently. Apparently, I had forgotten another aspect, is that basically when you make that call, I've spotted a hiker, that creates an additional flight immediately, instead of the drone waiting a little bit longer at the base. So apparently that is enough to offset the kind of reduction in clearing of fog of war that you had as a result of having to go to the same place again. Is basically you have more flight, and that compensates for it and actually makes it better. Now between 20,000 and 30,000, I only have bears. And there is what I expected to see. You have got the fog of war goes up again. Why? Because in this case, the drones are not just sending a message home to say, I've seen a bear. They also stop exploring and they hover over it. And that means that they effectively cannot complete their patrol. So then you can see why that would actually be, again, have a negative impact on the amount of fog of war, increase the amount of fog of war. And finally, in the last 10,000 time steps, I have both hikers and bears. And then it seems like the effect of hikers is basically, more stronger than the effect of bears, because it's essentially the same as between 10,000 and 20,000, which again is interesting because it's difficult to understand. Why is that? Because the bears are still there. There are exactly the same number of bears in that part as there was in the part before. So you should have the same effect, but you don't. So why? And the answer is the next slide. So basically, this is the fraction of time that hikers, that's the blue points, and bears, that's the orange points, were tracked for the time that they were in the park. And what effectively happens is that in this case, so of course the hikers are never observed they are observed regularly, but not for long, because you don't hover over them. You just go back and spot them again. So you see them many times, but most of the time they are not being monitored. But the bears are meant to be monitored as long as possible. So it should be closer to 1, which is effectively what you observe. But what you see here is that between 20,000 and 30,000, the swarm is actually doing a pretty good job at following the bears. So this value is quite high. The average is the dotted line in the middle. So effectively, there are enough drones in my system to monitor the bears, which means that these drones are effectively taken out of the exploration task to actually monitor the bear. And that means that the fog of war can increase because they're doing less good job at exploration. However, when I reintroduce hikers, some of the drones are distracted from the bear and find the hiker first. And so the monitoring of the bear is not as good, which is why the value of the orange dots plunges. So that means that effectively there's a kind of weird side effect whereby because the swarm becomes less good at tracking bears, which it's supposed to do, it becomes better again at exploring. So, you know, you've got all of these trade-offs that your system generates as a result of applying these simple algorithms that you have to balance against each other in order to get the best possible behavior. Finally, conclusions. So I hope that I have at least convinced you in part that wild swarms could be a viable option, at least for medium-term operations. So what I mean by that is that over the very long term, there are still things that the autonomous wild swarm will not be able to do. So for instance, they will still need to be maintained. At the moment, with the level of technology that we have, it's very conceivable that the swarm can manage the recharging and the division of labor and that sort of things. But when a drone breaks down, it's not going to repair it. For that, you will need to send a technician on site. To some extent, the collective intelligence is able to mitigate that because, as I showed in the demo, if you remove a drone or if you add a drone, it will use it as it can. So even if you start with 16 drones and you're left with 12, you will still do the best you can with 12. But eventually you will run out of them. And then you need to send someone on site to actually replace them or repair them. Another thing, the first point that I didn't mention, which is interesting, is that at the moment, the system does not require any communication for exploration after takeoff. The flight plan is generated before takeoff in the base, so no wireless communication required. And then the drone executes the flight plan and comes back to land. And at that point only, it uploads the information. So there's no wireless communication involved whatsoever. However, of course, when you have the spotting hikers and bears and sending information to base, then you will require some wireless communication. But it's important to understand that some of this mission could be executed without any communication during the flight. So essentially, the whole collective intelligence phase of planning the flight is effectively simulated at base before the drone actually takes off. So you don't need communication or radio control for your drones after that. Of course, this is making the case for future work. So technology would benefit from more algorithm development, new concept of operation, and many more numerical experiments and analysis to continue to explore the dynamics of that system that I mentioned before. Open questions. Could the mission be extended beyond maintaining situational awareness? At the moment, I've only talked about observation, but no action. There's no actuation in my system. You see the bear, you monitor the bear, but you don't, release a kind of bear spray to chase him away. So there is also the possibility that we could add actuation in the system and be able to do something about an event that is important, like a fire started. You might want to do something about it. In that sense, would actually heterogeneous swarm make more sense? Because you can imagine that in many cases, a drone that is good at patrolling and collecting information about an environment might not be the best equipped to take care of the event that it just noticed. For instance, again, fire management. Drones are light things. They cannot carry an awful lot of water or even fire retardant powder. But they might actually raise the alarm, and a ground robot that is basically a big tank of water could be dispatched on the area. So that was the kind of thoughts I wanted to share today. Thank you. Sorry for extending beyond the limit, but we were supposed to chat, so we can chat now.